Let's analyze the given 2 by 2 matrix game for players A and B. The payoff matrix is B1, B2, A1, 25, 5, A2, 10, 15. This matrix represents the payoffs to player A. In a zero-sum game, the payoffs to player B would be the negative of these values. However, the problem statement doesn't specify it's a zero-sum game, so we treat it as a general 2 by 2 game where the values in the matrix are the payoffs to player A. 1. Existence of saddle points. Maximin equals minimax. To check for a saddle point, we need to find the maximum value for player A and the minimax value for player B. For player A, maximum strategy, player A seeks to maximize their minimum guaranteed payoff. If A chooses A1, the minimum payoff is min 25, 5 equals 5. If A chooses A2, the minimum payoff is min 10, 15 equals 10. Player A's maximum value is max 5, 10 equals 10. This occurs when player A chooses A2. For player B, minimax strategy, player B seeks to minimize player A's maximum possible payoff, assuming player A plays optimally. If B chooses B1, player A's maximum payoff is max 25, 10 equals 25. If B chooses B2, player A's maximum payoff is max 5, 15 equals 15. Player B's minimax value is min 25, 15 equals 15. This occurs when player B chooses B2. Comparison. Maximin for player A equals 10. Minimax for player B equals 15. Since maximin 10, nec minimax 15, there is no pure strategy saddle point in this game. This implies that the game will likely have a mixed strategy Nash equilibrium. 2. Finding mixed strategies for players A and B. Since there is no pure strategy saddle point, the players will resort to mixed strategies to maximize their expected payoffs. Let P be the probability that player A chooses strategy A1, and thus 1P is the probability that player A chooses strategy A2. Let Q be the probability that player B chooses strategy B1, and thus 1Q is the probability that player B chooses strategy B2. For player A's mixed strategy, player A chooses P such that player B is indifferent between their strategies B1 and B2. This means player B's expected payoff from B1 equals their expected payoff from B2. From player A's perspective, expected payoff for player A when B chooses B1 EA of B1 equals 25P plus 10 1P. Expected payoff for player A when B chooses B2 EA of B2 equals 5P plus 15 1P. Setting them equal, 25P plus 10 to 10P equals 5P plus 15 to 15P. 15P plus 10 equals minus 10P plus 15. 25P equals 5. P equals plus 5. 25 equals plus on 5. So player A's mixed strategy is to play A1 with probability fraction 5 and A2 with probability 1 fraction 5 equals frax for 5. For player B's mixed strategy, player B chooses Q such that player A is indifferent between their strategies A1 and A2. This means player A's expected payoff from A1 equals their expected payoff from A2. Expected payoff for player A when A chooses A1 EA of A1 equals 25Q plus 5 1Q. Expected payoff for player A when A chooses A2 EA of A2 equals 10Q plus 15 1Q. Setting them equal, 25Q plus 5 to 5Q equals 10Q plus 15 to 15Q. 20Q plus 5 equals minus 5Q plus 15. 25Q equals 10. Q equals frac 10. 25 equals frac to 5. So player B's mixed strategy is to play B1 with probability frac 5 and B2 with probability 1 frac 5 equals frac 5. 3. Find the expected value of this game for both players A and B. In a general sum game, the expected value is usually considered from the perspective of the player whose payoffs are in the matrix. Here, the payoffs are for player A. The expected value of the game for player A when both players play their mixed strategies, can be calculated using either player A's indifference condition, using player A's expected payoff if A chooses A1, which should be equal to the expected payoff if A chooses A2 at equilibrium. EA equals 25Q plus 51Q. Substitute Q equals frac 5. EA equals 25 left frac 5 right, plus 5 left 1 frac 5 right. EA equals 25 left frac 5 right, plus 5 left frac 3 5 right. EA equals 10 plus 3. EA equals 13. Alternatively, using player A's expected payoff if A chooses A2, EA equals 10Q plus 15 1Q. Substitute Q equals frac 5. EA equals 10 left frac right, plus 15 left 1 frac right. EA equals 10 left frac 3 5 right. EA equals 4 plus 9. EA equals 13. The expected value of the game for player A is 13. Regarding player B's expected value, the problem statement does not provide the payoff matrix for player B directly. In game theory, if the game is not explicitly stated as zero-sum, the payoffs in the matrix are usually just for the row player, player A in this case. To find player B's expected value, we would need player B's payoff matrix. However, if we assume this is a zero-sum game, meaning player B's payoff is the negative of player A's payoff, then player B's expected value would be EB equals EA equals minus 13. Without the explicit payoff matrix for player B, we can only confidently calculate the expected value for player A.